Decision of the canonical equations of the force method not determining the diagrams of efforts in the statically indefinable mechanical system. It's article number 3.5 from the book Mechanical Systems Calculations of the Marine Facilities. In the article 3.4 of the book, we considered the determining the factors and the three terms of the canonical equations because we have assigned a statically indefinable system. So for the system, like indicated on the figure 3.5.1, we have the links. We have supporting links in the point B. We have two, and we have rigid embedding in the point A, and if we have external load F, the sizes of this is a rigid corner in the frame, the hinge here in the B, and the length of the vertical part of the beam is L, and the horizontal part is L2. So the force F applied in the middle. So from the corner, from the embedding, the distance to the application point of the point F is L divided by 2. And the system assigned is statically indefinable because we have three balance equations on the plane in flat state here, and we have 5 unknown for the subject to find all the support reactions. So we have 3 unknowns in the point A, the two components of the resultant force of the reaction and in the point A, and one rotating moment in the point A. And we have two components of the resultant force in the point B. So together we have 3, and 2 we have 5, and only 3 balance equations. But to decide this kind of the mechanical system, it is to find the support reactions, one of two main issues of the statics. We have to consider this frame as deformable, and we have to develop for the system the canonical equations. For example, we can use the force method widely used. This is the we cut off two of the exit of the unnecessary support reaction. Could be directions in the point B, could be another supports we can remove, or just only part of the support. So determine the support as the support with less number of the reactions. Like for the point A, we can make a change, for example, to put instead of the point A the sliding hinge maybe. But anyway, we decided to remove the supporting links from the point B and to have the main system. Due to that, we substitute in the point B the cut off supporting links by the reactions in the supporting links to find this magnitudes of these two components of the reaction. The fixed joint B cut out, applied the forces to the end of the frame of statically definable frame. In this approach, we say main system. We use the canonical equations. It could be the canonical equations of the forces method, as we substitute the cutoff links by the forces. And in the assumptions of the force method, when we apply the forces to find the forces, what is magnitudes of forces x1 and x2, we have to find the magnitudes of the forces which satisfy zero displacement of the point B with the cutout supporting links in the direction. For example, for the first canonical equation, it could be direction of the force x1. And we have to find the magnitudes of x1 and x2, which satisfies the condition of equality to zero of the displacement in the direction of the force x1 when we cut off the support. The same we have, and as well we have one free summand of this equation. This is a term of the uppercase delta the term of the action of the external force, external load to the applied to the frame. How do this impacts the displacement in the point x? So we consider all the displacement in the point B in the direction x1. We consider the displacements total of each loads applied to the mechanical system, including the load subject to find the loads of the cutoff links of support reactions. The second is the same condition, the canonical equation of the force method. So equality to zero of displacement in the direction of the force x2 applied here instead of the vertical supporting links in the point B. So this is system of the equations. We have to find the factors to each magnitude of the forces of in the support B subject to find, and we have to find the free terms of these canonical equations. In the article 3.4, we did find the factors, coefficients of the canonical equations of the force method and the free term as well. And this is the sequence, the list of the got in the previous one article factors. We used the Moore integral, so-called method of Moore integral, to find the displacement of unit force applied in the direction one. How does it impact the displacement in the direction one of this force, unit force applied in the direction two? How does it impact to the displacement lowercase delta, mean the displacement on direction of the unit force, the equality with the displacement with indexes q and in the displacement of unit force in the second direction due to the force applied in the fourth direction. So this is the lower of the reciprocity of the displacements if we have the same indexes but to change it. The displacements are equal, and we have the displacement of the second in the second direction of second force applied instead of the supporting links, but in the second direction too, and we have the displacements got as well by the decision of the Moore integral in the first direction on behalf of the action of under the action of the force external load assigned F, and in the second direction the displacement under influence of the force external F. So when we substitute this all summands and factors in the canonical equation of force method, and when we just cancel, when we cancel the common factors in these canonical equations, because which is a common factor in each of the factors listed here in the summands, free summands in the canonical equation, these common factors are the fraction, and in the nominator here of the fraction we have L cubed, and in the denominator we have E the elasticity modulus, and I is a moment of inertia of the cross section of the frame. So when we cancel this in the equation, so we have finally the canonical equations in the indicated form here in the slide for the fraction 4 divided by 3 multiplied x1 minus the fraction 1 divided by 2 multiplied x2 plus fraction 1 divided by h multiplied f, etc. Second one equation. So we can decide this equation. That's understandable how to do that. We can just deduct, for example, the force under the subject to determine the x1 from the first one equation, due to redetermine this x1 by other force subject to find x2 and external load F, and substitute in the second equation, can find next from the second equation the force x2 and substitute back again in the first equation and find the force x1. It's not a big deal, and I will not go in the detail. So, but actually the force, the reaction x1 have to be after decisions of the canonical equation, if mathematic transform and canceling the common factor, etc. The decision of the canonical equations is that x1 equal to 0.0536 multiplied by f, and x2 equal to 0.3229 multiplied by f. So this we have three extra variables, and to find all others variables we can use in the considering the main system as a statically definable system loaded by external force and loaded by the GOT support reactions in the support B, cutoff support B. Okay, so the next question we have to decide is the creation of the diagrams of bending moment, shearing forces, and longitudinal forces in the elements and segments of the considered frame. We can use previously got diagrams of the bending moments of under the influence of the in the elements and the segments of the main system did of the assigned system by the cut of the supporting links in the point B. We did this manner. So the bending moment diagrams of the unit forces indicated here on the figure 3.5.2 A and D. This is a what is the diagrams. But we have first all to improve these diagrams. What is improvement? Improvement is indicated here on this last equations on the slide. So as we have unit force, the bending moment diagram is as indicated in the definite one, figure 3.5.2 D and A under action of the unit force. But after decision of canonical equations of force method, we determine the magnitudes of the forces not equal to 1. So we have find that x1 is 0.0536 multiplied by f, and x2 0.3229 multiplied by f, and no 1. So we can do the improvement of the bending moment diagram. So after the improvement, after the substitute of the magnitude of the force, proportionally the diagram will be looks like the same. I mean the shape. The diagrams B instead of A and C instead of D. But the same shape as the diagram and direction of the unit force, diagrams of the bending moments, but of the another magnitudes. So magnitude corresponds to GOT and to the GOT magnitudes of the forces and the supports x1 and x2 proportionally. So the maximal instead of L is the magnitude of the diagram adduction of the unit force, as the length of the segment is L. So here we have 0.0536 multiplied by F. And this is evenly distributed bending moment under the force X, but not equal to 1, but equal to 0.0536. And the same as we can take the diagram of the bending moment and action of the force, unit force in the direction of the force x2, which by which we substitute the cutoff second link, second supporting link in the point B of the assigned diagram when doing the in the assigned system of mechanical system when doing the main mechanical system statically definable. So having the magnitude of the force, not one, but we have another one magnitude, 0.32229 multiplied by f, and we have the magnitude of the second 3229 by f. Excuse me, just a little bit, I can check. Yeah, this is the magnitude of the force x2. This have to be multiplied by f due to the this decision. Actually, probably here is a mistake, 3229, but we have here 3929, but maybe this is one have to be 2. Yeah, but it's so much important to explain the concept. Okay, so after, I'm sorry, this the second one, this is correct, but 3929 have to be here in the x2. Okay, next we can do the final diagram, the bending moment of the superposition of all considered diagrams of the force in the absent supporting links. When we do the it corresponds to the force in the support, actually, due to the compatibility of deformation concept provided by the use of the canonical equations of the force method. So, and when we can do add this all three diagram and the projection connection, so for the first segment, the diagram of the external force we had beforehand when we do the determination of the free summons of the canonical equations of force method. So here, this part of the only is not zero. We put it here for the first one segment of the mechanical system. And for the second one system, we have to consider that on the left, the magnitude of the diagram of the, on the left point in the corner, the magnitude of the diagram of the external force, bending moment and direction of the external force is 0. Magnitude of the diagram of the bending moment and direction of the force, second force, got here, which we did corrected a little bit as 0.3929, not as indicated here. This is a little mistake in the second, and the second data, 3929, yeah, have to be. And we next in the projection connection, on the left point, we put the magnitude of the diagram FM1, and these 2 points we have to find as the total of these considered all diagrams. So for this definite 1 point, we subtract from this. This is diagrams of other signs. As for developing of the bending moment diagrams, the rule of signs of bending moment is relative. So for definite assignment, we just have to remember about the direction of the application of the shearing forces and bending moments we use as a positive one. Usually in mechanics, we use a positive one, bending moments rotating the mechanical system counterclockwise. But for definite one decision, perhaps the positive, we can take the clockwise rotation of the system. So this will be the diagram determined on the stretched fibers of the element mechanical system. So this diagram we consider it positive, rotating clockwise relative to the support, and this one evenly distributed with the same magnitude as the maximal for the previous one segment as a positive 2, but this we consider as negative. So and the when we find the total of these two diagrams, this we consider as negative, this we consider as positive, this we consider as, excuse me, rotating clockwise. This we consider positive. The diagram of bending moment and action of the external force. This we consider negative, and when we consider together for the right one point is point A in the sign system, bending moment is total of this magnitude 0.5 multiplied by F multiplied by L. This magnitude is 0.0536 multiplied by F, and this magnitude, which is the 0 as well, 3929 multiplied by F. So considering this all together, yes, we have the bending moment diagram magnitude as equal to 0.1607 multiplied by F multiplied by L. Yes, and here we have to put one more factor as multiplication by L, exactly, because this is a magnitude of the force, but the arm of the action of force is L. L is length of the segment. Okay, the same as here. A little bit improvement have to be here to correction. So multiplied by L multiplied by L2, because this is the diagram of the bending moment. And after and next we have the diagram already there of the bending moment action on the mechanical system assigned such and definable. And we can do the check of the correctness of creation of the diagram of bending moments. To do that, we can find the as a criterion of correctness as equality to 0 the displacement in the point A. The point A is the left one and lower point of the mechanical system. It have to be equal if we load the mechanical system by the God diagram of bending moments acting on behind of the support reactions x1 and x2, and on the external load force bending moment to do this all diagrams correspond to the displacement in the point A equal to 0. What is this? What is the displacement? We say about the generalized displacement, considering the displacement as we indicate as S is displacement in two directions, displacement, but just the algebraic total of displacement. So we have got in the previous article 3.4 the diagram of bending moment of unit forces, and we have this diagram we have on the unit forces. If we assume that we look for the displacement in not the force direction like uppercase delta 1, and not we assume they're looking for the second displacement second direction uppercase delta 2, but we consider the general displacement as an abstract concept of the displacement in considering the superposition of the displacement in other directions of the elastic mechanical system, proportional elastic mechanical system, as each displacement is total of delta 1 plus delta uppercase 2. So this direction we say is not the first, not the second, but number S index of the generalized direction. So for this direction in the support B, left one support B, we have to consider this diagram got in the previous one article of the bending moment action in the main system of under the action of the forces on the this and B of this mechanical system, but not in the direction of the first force and in the second force, but in the generalized direction. We say direction S, which is equivalent to the algebraic sum, algebraic total of the displacement in the first and second direction. It's abstract yet, but we actually we cannot find the total of two vectors. They are not of the, if they are not collinear, because it's not the magnitude of the total of two vectors. If they're not collinear, we have to consider the angle of the inclination between the vectors. But we are talking not about the geometry, we're talking about the elasticity. From the elasticity point of view, we can consider this generalized displacement of this one, of the same mechanical system, but in other directions. Yes, and to find this all, we have to consider as well, and we use this diagram as here in the integrand, the moment diagram of the bending of forces caused the on the bending under unit forces in two directions of the applied support directions instead of the supporting links. And we have this one diagram. This one diagram is in the integrand, the second factor in the numerator here in the integrand. So to decide this more integral, to decide, we can use considered in the previous one article 3.4, the Vereshchagin rule, and as well we can use, we do not use Vereshchagin rule, we use the opportunity of the method of the finding the integral of product of functions if this is two linear functions. For example, we can here the example of two linear functions, f1 and f2, how to find the integral in the definite limits of these functions, the product f1 by f2. The product, if the functions are linear, equal to the product L divided by 6 and multiplied by, in the brackets, 2 by A, the A and C, two left ordinates of each of these trapezoids, linear. It could be a triangle. In this case, ordinate have to be equal to 0 if trapezoid definite magnitude of the ordinate is A, maybe C, plus the product factor 2 by B by D is the right one, ordinates of this trapezoid and the projection connection we consider, and plus the A multiplied by D is a cross multiplication, A by D plus B by C. Yeah. So this is the known formula how to find the integral of product of two functions used in the mechanics as well. And as these two functions, we consider the function of the bending moment got for the considered mechanical system as a total of 3 diagrams of bending moment and action of the force in support force x1 and the bending moment of the force x2 and the external load, and we have the final bending moment diagram, and we have to check it. And this diagram we have to product by the segments of the mechanical system. We have to product by the diagram of the bending moment of the same system and direction of the generalized force under action which cause under unit forces in the direction which we assume as the abstract S direction. We did this. The S direction is the when we find the uppercase delta S is equal to the total of uppercase delta 1 plus uppercase delta 2. This is orthogonal perpendicular displacements, but within concept of the elasticity, we consider this as a common deformation. And this is the bending moment corresponds of unit force of unit force in the direction of the generalized we indicate by index S. So using this formula for the integral of the product of two functions, linear functions, applying this formula by the interval for the first segment, for the second segment between this point and this point of the corner of the diagram and this point of the corner to the embedding here. So we have three summands here when determining the product of two functions. Function of the diagram of the bending moment of unit force, finding the applied in the generalized direction, we indicate S, and product by M. M is the good final diagram of the bending moments here. So using this formula for the use of how to find the integral product of functions of the trapezoid or any other linear, maybe triangle diagrams. So we find that after the substitute of the magnitudes we can find that the more integral for these two diagrams for the considered mechanical system is 4.2 multiplied by 10 in the power minus 6. In the power minus 6. So this is about a very small number, is about the equal to 0. So we decide that yes, we find the support reactions and we do create the diagram of the bending moment correct. So this diagram satisfies the displacement of the support reaction B for 0 in the what direction? In just abstract S direction, which covers together direction in the direction of the application of the first and the second components in the support B, but any generalized concept of the displacement between them two, which correspond with this diagram of the bending moments, which arise under action of the forces in this abstract direction S. So, and now, after got of the and the checked correctness of finding diagram of the bending moment, we go to next step, how to find the diagram of the sharing forces, transverse forces action on the mechanical system. We to do that can use the dependence, the law, the diagram of the bending moments and the diagram of the sharing transverse forces are interrelated as the integral and derivative. So the diagram of the bending moments is the integral function of the diagram of the sharing force, and that accordingly the diagram of sharing force is the derivative dependence on the diagram of the bending moment. So we have diagram of the bending moment, how to do the diagram of the sharing forces. If we consider rotating this one as the so the how to find the derivative for this one diagram. The derivative is a tangent of the inclination of this diagram. Tangent is equal to the proportion of two legs. So if we consider the diagram as a right angle triangle, so this leg is 0.536 product by F by L, but the leg is L, so the force is 0.536 product by F. So to find that, we have to take for linear diagrams, we can take the magnitude on the left end, on the right end. We can find the subtract of the right one end, or subtract the left one end, subtract from the right one end, and the result divide to the span of the leg. So this we have that the shearing force, transverse force, is the subtract of the magnitude of the bending moment on the left point on the first segment of the mechanical system, and the point B minus the the moment on the right one point here, minus 0, 0 is the bending moment in the left one point here, left 1.0, and finally we divide this by L, length of the segment, and we have that the shearing force is minus 0.0536 multiplied by F. This is transverse force here, and we have now the distributed force along the first segment of the sine system, so this is even distribution of the transverse force. So, but next, in the point, in the segment from the corner here to the point of the application of the transverse force, we can take the magnitude of the bending moment here. We have the magnitude. Subtract the magnitude, negative, another sign magnitude, we compare with this one. Subtract the magnitude of the bending moment on the left and divide for the length of the segment. And we can find the tangent of the angle of the inclination of this one line. So, and we have, considering the adopted law for this definite fine assignment, law of the sines, it will be positive due to from the positive magnitude of the bending moment, we subtract negative magnitude of bending moment. So the value upper one is negative, lower one is positive. Rotating clockwise is positive, rotating counterclockwise negative. So this is rules of the sines applied for definite one assignment, which we consider here. And when we next divide by just a half of L, just half of L is length of the segment. Segment of the equal of the linearity before there's one corner in the diagram. So, and we have that the shearing force equal to 0.393 F. This is a magnitude of the shearing force in this full segment of the upper one rod of the mechanical system assigned. And on the last segment, we can find here as well. So we have on the right side is 0.1607 multiplied by F by L minus the magnitude on the left one side of the considered segment, 0.1429 multiplied by F multiplied by L, and divided for the 0.5 multiplied by L is the length of the segment of this linearity of this diagram. So we have as the right one, we have negative, so rotating. So we have negative here, 0.16.7 product by F by L, and we minus positive, so two negatives we have finally in the numerator of this fraction, and divided by length of this segment. Of a small segment, half of the rod length of the considered frame is minus 0.607 multiplied by f. And so we have the diagram of the transverse forces. And this is forces rotating counterclockwise with a minus sign, rotating clockwise is a plus sign, so we have to be very attentive. We compare the got forces to the rule in the definite one assignment for the considered assignment of the rules of which is a positive, which is negative signs of the shearing forces and bending moments. So, and we have to find as well the longitudinal forces acting in the elements of the mechanical system. To do that, likely we have to use the cut of the rigid knot, for example, here. And in this definite one knot, we can consider the balance equation for this knot. And we have two forces transverse in the knot applied. One force is directed counterclockwise, we say 0.393 multiplied by f, and the force rotating counterclockwise 0. Directed from left to right 0.0536 multiplied by f, and we have two forces of which are the longitudinal force in the rod number 2 and longitudinal force in the rod number 1. Considering the equality to 0 of projections of all forces on the horizontal vertical axis, we can find that force in the segment first of the considered mechanical system is minus 0.393 multiplied by f, and the force in the segment number 2 is minus 0.0536 multiplied by f. And is this due to the balance equation of the cut-off knot of this rigid corner from here? And as we have no longitudinal distributed force in the segments of the mechanical system, this is the evenly distributed diagrams. No linearity, as just only even distribution. And questions and comments. The solving of system of canonical equations of the forces method. To solve the canonical equations. Yeah, first we had a little bit simplify. We can cancel out the common factor from the canonical equation a little bit, and the simple from the first one we can, if we have only two canonical equations. From the first one we can derive one unknown variable, substitute on the second one, and after that we can derive the second one variable from the second equation and find it, and substitute in the first one and find the first one variable. Variables are unknown variables in the canonical equation. They're subject to find the forces in the cut-off and in the cut-off unnecessary links due to we have the excessive forces instead of the links when creating the main system of the assigned statically indefinable system, and the main system is statically definable. So after that we find the forces, and after they can use the balance equations, because when we find considering the system deformation, two extra forces in the cutout unnecessary connections. So after that we can use the balance equation to find all others, and to draw up the diagrams of the bending moment, shearing forces, transverse, and longitudinal forces in the elements of the mechanical system. 3.5.2. The use of diagrams of bending moments under unit forces and found values of directions and supports. The forces in replaced connections to determine diagrams of bending moments and elements of given statically indefinable system. To do any of action, for example, to determine the diagram of the bending moment after finding after decision of the canonical equation and finding the unknown variables as which are the support reactions in the cutoff link, supporting links, we can determine the diagrams of the bending moments and other diagrams, like the diagrams of the shearing transverse forces and the diagram of the longitudinal forces. But to find we use a property of the superposition of the diagram of the bending moments. If we have diagrams of separately found the support reactions and the diagram of the external forces assigned originally, we can find the resulting diagram of the bending moments. But first of all, we have to improve the diagram of the bending moments of the mechanical system under action of the unit forces, because we, after decision of the canonical equations, did have the magnitudes of the forces of the support reactions, and they are not unit, but we have to proportionally correct the diagram of the bending moment of unit forces to have the diagram of bending moments and the action of the got magnitudes of the support reactions. 3.5.3, checking the correctness of final diagram of bending moments by finding the displacements in the replaced connections of a statically indefinable mechanical system, which must be equal to 0. As we have after the creation, after determination, we have the final diagram of the bending moments of the external load and the support reactions acting on the mechanical system. We can check the correctness of finding this diagram. How to do that? The displacement of the the displacement of the points in the supports have to be equal to 0. Especially in the supports, we cut off when determine the main system statically definable of the statically indefinable assigned system. So in the directions of the support reactions, we can we may do check and find the displacement under the action of the bending moments in accordance with the code diagram of the bending moments when under action of the external load and found support reactions. To do that, we can use more integral to find the displacement. If the displacements are zeros, the check of correctness is good. But even more than that, instead of the checking of displacement in 2 or more directions of the cutoff supporting links due to the number of the statistical indefinability of the assigned system, we can as well consider the one general displacement. It has to be equal to 0 if we consider any abstract concept of displacement, which is a total of displacements of just the algebraic total of displacements in the 2 directions of the cutoff connections. All those directions are perpendicular to each other, are not collinear vectors, so we cannot find the magnitude of the vector just by algebraic total if the vectors are not collinear. But this is the concept of the elasticity. So if each of summand equal to 0, the total equal to 0. This is what. So we have the diagram of the bending moment corresponding this concept as the total of diagrams of the geometric total of diagrams of bending moments under action of the forces in the cutoff connections and when we find the generalized diagram by yeah, by the summarizing of these diagrams. So we assume that we have the any like the displacement have to be common, and this have to be equal to 0 if each of the summands is equal to 0. 3.5.4. A universal check for equality of conditional displacement to 0 is which is determined using a diagram of bending moments, which is the sum of diagrams of bending moments for each of the found forces in the replaced connections. Yes, it is. So what we talk about is that instead of the of checking the equality to 0 of displacement in each of the cutoff support links, we can find the we can check the equality to 0 of this total of the displacement in this two or any number of directions in accordance with the static indefinable system. In the considered system, we have only 2 degree of static indefinability, so we have 2 variables, and but in any case we can have many. And 3.5.5, the use of formula of trapezoid to find the integral of product of functions. Sometimes instead of to find the more integral, we have to find the integral, and the integrand, we have the product of 2 functions. To find the product of functions, we sometimes can use the Vereshchagin rule, as we did in the previous one, article 3.4. But if we under the if in the integrand we product 2 linear functions, so we have trapezoid formula to find what is the integral of the production of 2 linear functions. So we can use it. 3.5.6, the shear forces diagram determining by differentiating the diagram of the bending moments. So when we have the diagram bending moments, we can find the diagram of the shearing forces. This is not difficult to do if the diagram of bending moments is linear, as in the considered case. And the shearing force is a derivative of the bending moment for each of the segment of the considered mechanical system. So the tangent of the angle of the inclination of the diagram of the bending moments, this tangent corresponds with the magnitude of the diagram of the shearing force. For the linear bending moment diagram, this magnitude of shearing force will be evenly distributed. So constant angle of inclination, constant tangent of this angle. And we use by digital differentiation. Digital differentiation is we can take for the linear functions, we can take the magnitude of function on the right one end of the considered interval minus the magnitude of function on the left one and of this, then this subtract of left one and magnitude of the right one. Next we have to divide by the length of the interval. This we will have the magnitude of the derivative. So for the bending moment diagram, this is magnitude of the shearing force. 3.5.7, the longitudinal diagram determined by cutting out nodes and drawing up equations of balance of internal and external forces. Yeah. When we have a diagram of the shearing forces, it's not difficult usually to find the diagram of the longitudinal forces if we do not have the distributed longitudinal force, for example, and we just assume that the diagram of the longitudinal forces are linear, diagrams are linear by the segments of the mechanical system, and to find these linear functions of the diagram, we need only to have the magnitudes at the ends of each considered interval of the diagram of the longitudinal forces. And these ends we cut out as the nodes of the mechanical system. and consider the balance equation for the nodes. And usually in these points in the nodes of the mechanical system, we have the projection of forces of the transverse force and longitudinal forces. And due to the use of the balance equation for the cut out nodes of the mechanical system, considering the transverse forces, sharing forces, and the longitudinal forces, we can find the longitudinal forces. And the linear diagram of the longitudinal forces is just a line through the found magnitudes, points of the magnitudes of the diagram of the longitudinal forces. Thank you.